In this problem, we'll use a mixture of calculus and algebra to sketch the graph of a rational function. We'll start by looking for the roots of the function. Since it's a rational function, it'll make sense to look for vertical asymptotes and horizontal asymptotes. After that, we'll use calculus to figure out where the function's increasing, decreasing, concave up, and concave down. We then just have to check where all the critical points are, exactly what the xy coordinates are, and where it's concave up and concave down. And then an easy step, figuring out the coordinates of the critical points. It wasn't a step on my list, but it is awfully helpful if before we get started, we factor the rational function like I've done right here. To find the roots of the function, we have to set the numerator equal to 0. And that just gives us x equals 0 and x equals 4. Vertical asymptotes often occur where the denominator is equal to 0. In this case, at x equals 1. When we start to look at the limit as x goes to 1 from the left, well, plugging in 1, we get 1 times negative 3, that would give us a minus 3 on top, and a 0 on the bottom, and that tells us, yes indeed, we're going to have some kind of asymptote. And so we do a little bit of scratch work, and we say, alright, if x is a number that's just a tiny bit smaller than minus 1, then x is going to be a positive number. The quantity x minus 4 is going to be something negative, and x minus 1 is going to be negative, but we square it, and that means that that fraction is always going to have a positive value on the bottom. All told, every number in that fraction, as we're taking this limit, is negative. We have an asymptote, and so we must be going to negative infinity. So let's write that in a better way, just saying that the limit is negative infinity. If we do the exact same computation with x going to 1 from the right, we find out that the answer is the same. The horizontal asymptote is easiest to locate using the unfactored form of the function. The highest power we see in that expression is an x squared, and so to get from my first equation to my second equation, all I'm doing is dividing every single term by an x squared. Every term, except for the two leading terms, goes to 0, and we see that we've got a horizontal asymptote, at least off to the right, of 1. And you can double check that if you take the limit going to negative infinity, you're going to get the exact same answer. To figure out where our function's increasing and decreasing, we need to use the first derivative. Now, you can just trust me that that's the right answer, or you can check that my computation worked right. Classic low d high minus high d low over low squared. The interesting part here is that when I went from my first expression to my second expression, I was looking for the quantity x minus 1 to be popping up. There's going to be a little bit of canceling we can do that gets us to our final answer. Our cleaned up version of the derivative tells us we have a critical point at x equals minus 2 and a critical point at x equals 1. And then we just plug in some test values like x equals 2 to tell us that all told, when x is bigger than 1, the first derivative is positive. Between minus 2 and 1, the first derivative is negative. And for x less than negative 2, the first derivative is positive. This tells us we have a local maximum at x equals minus 2. You might think there's a local minimum at x equals 1, but that's, of course, where we had the vertical asymptote. Just as before, you can either trust me that I computed the second derivative correctly in order to find concavity, or you can double check this formula. Starting with the first derivative, do the classic low d high minus high d low, and you'll once again notice there's a lot of x minus 1 terms you can get, and that'll clean up to give you the answer I've given above. The cleaned up version of the second derivative lets us know that there's a critical point at negative 7/2 and at x equals 1. Just testing values, we see that for x values bigger than 1, the second derivative is negative, Between minus 7 halves and 1, the second derivative is negative, but less than negative halves, the second derivative is positive, which means that we're concave up, concave down, and concave down. To locate all of our critical points on the graph of the function, we need to remember to plug them in to the equation for the function. So the y value when x is minus 2 is gotten by plugging a minus 2 back into the original function. And then doing enough arithmetic to get us down to 4/3. You figure out all the other values that I've indicated here the same way. Okay, let's start trying to put all of this information together. We've got roots, we've got asymptotes, we've got information on the first derivative, which, if I remember right, was going positive, negative, positive, and on the second derivative, which was going positive, negative, negative. I have just put all the basic information into this graph on the right, and let's start thinking about what's occurring for values less than negative 7 halves. We know that the function is increasing, we know that it's concave up, and we remember we have this horizontal asymptote. Between minus 7 halves and negative 2, we're still increasing, but we've switched concavity. And then we begin decreasing, staying concave down. For values of x bigger than 1, we've got to come off of this vertical asymptote, be increasing, and be concave down. So the graph of this function looks a little bit like the sketch we just drew. And now that we've located all of these interesting features, I can use a computer to draw the graph you see over here on the right, which I think is even better than the graph that I did by hand using all the information that we'd figured out as we went along.